So this is our first lesson in Unit 1617, which is all about the normal distribution. And fittingly enough, our first lesson is an introduction to the normal distribution. So by the end of this lesson, you just want to be familiar with some of the basic properties of the normal distribution. And then at the end of this, we'll do a little investigation together where we look at the relationship between the binomial distribution and the normal distribution. So what do you need to know about the normal distribution? Well, the normal distribution has a very specific shape, and it looks kind of like that. Okay. When we were talking about distributions, we gave this kind of shape a particular name. We said it was mound-shaped, or I might have used the term bell-shaped, or something like that. But these are just sort of more common names for what we call the normal distribution here. So if we've got a distribution like this, way back when we were talking about distributions, we said that distributions like this had a mean, a median, and a mode that were all about the same thing. Okay? Mean is very similar to the median, very similar to the mode. And where that mean, median, or mode occurs is right in the middle of our distribution. So I'm going to label this as x bar for our mean. Okay. So we definitely use the word symmetric when we talked about distributions like this. So this is symmetric about the mean. The mean divides this thing in half. So what are we graphing when we have something like this? On the x-axis is any old thing that we want to be measuring. Okay? And the vertical axis, as with other distributions, is the number of things that have that particular value, or sometimes we can use this as, think of this in terms of the probability that something is going to take on that particular value. Because this is a nice smooth curve, the normal distribution usually applies to data that are continuous. Now, why do we care about the normal distribution? Okay. The normal distribution models pretty much anything that you're going to measure in a physical situation. Okay? It is by far the most common distribution that you're going to encounter out there. So most physically measured data follow the normal distribution. So think about things like measuring, I'll put the example down here. Let's say you were measuring height, or you're measuring weight of, let's say, a bunch of people. Okay? You are going to have a whole lot of people that are about average height. Okay? Maybe not exactly average height, but somewhere close to that average, somewhere in the middle. Okay? And then you've got a relatively few number of people who have extremely large values of height. These are like your NBA players, your 7-footers. Okay? There's a very small number of them. And likewise, you have a very few number of people who are extremely, extremely short, who are considerably shorter than the mean here. Okay? So you end up with a lot of things in the middle, a very small number at the very large or very, very small value. And as you go away from the mean, you get progressively fewer and fewer and fewer number of things that you're measuring. Okay? So you can think about this as measuring height, measuring weight. If you were trying to build something and you built it over, and let's say you were trying to cut a 2x4, so it had a length of exactly 2 feet, and you cut 50 of them, none of them would be exactly 2 feet. You would get some that were less, some that would more. If you were to measure all the heights, the lengths of them, they would follow the normal distribution. So it's an extremely common distribution, occurs just about everywhere. The other reason we care about it is the normal distribution can be used to approximate other distributions. And that's what we're going to look at in box B. We're going to look at how you can use the normal distribution to simplify some calculations that you would normally do with the binomial distribution. Okay? And that's a little bit tricky because we know that the binomial distribution applies to discrete data because it talks about a number of trials. But we're going to look at how that works in the investigation next. Okay? So these are the big properties of the normal distribution. So just to pick up on this, when we draw a normal distribution, we usually say that the area under the curve is 1. Or what we mean by that is that underneath this curve are all of the data that we have measured. Okay, 100% of the data falls underneath this curve. And we usually scale it so that the total area is exactly 1. Now, the normal distribution is described by just 2 parameters. Okay, just 2 variables in this thing. There is the mean, okay, which tells you where the center of this thing is. And there is the standard deviation. Deviation, right? Which basically tells you how wide this distribution is. So if we look at this graph here, we could start first by looking at, it's the blue curve on up here. It's labeled A on your notes there. This normal distribution has a mean value of 0, so it's centered right at 0 there, and it has a standard deviation of 1. If we change the mean to a mean of 1 and we keep the standard deviation the same, we're just shifting that curve over so that it is now centered at a value of 1. And that's what we have here in curve C. If instead we keep the mean exactly the same, the mean is 0, and we just make the standard deviation bigger, the curve gets wider. Okay? Area underneath the curve is still the same. And the big thing is that the shape doesn't change. Okay? It's always got that bell-shaped symmetric curve to it, okay? No matter how you change the mean or how you change the standard deviation. So what the normal distribution is it's kind of like a standard distribution that you use you can use for doing a lot of probability calculations. All right. Now there are some specific properties about the normal distribution that we're going to make use of when we do our probability calculations. And we can sort of summarize them if we look at sort of this graph here. And what they've done is they've taken our normal distribution here and they've drawn lines on it representing how far away from the mean you are. So they have labeled this line right here +1 sigma, which means a value right here is 1 standard deviation larger than the mean. And over here, -1 sigma means that you are 1 standard deviation below the mean. So this width right here is sort of ±1 standard deviation. So I'm just going to write that down. Okay, 1 sigma below x bar. This point right here, we are 1 sigma greater than. How much is that actually? Well, we don't know because the value of sigma is going to be different for different normal distributions. What these numbers inside here are telling us is that this tells us, this 34.13% is telling us that in this region, right in here, there is 34.13% of our data is contained in that area of the graph. Okay? And that is true of any normal distribution that you have. And because it's symmetric, if we go to the other side here, between the mean and whatever value is 1 standard deviation greater than the mean, that area in there has another 34.13% of the data. So between this line that represents 1 standard deviation below and 1 standard deviation above, we always have 68.26% of the data. is within 1 sigma of the mean. Okay? And that's true for any normal distribution that you have. And we can do the same sort of analysis if we go more than 1 standard deviation away, if we go to 2 standard deviations away. So this line right here would be 2 standard deviations below the mean. This would be 2 standard deviations above the mean. In between the two of them, we would have, let's see, 95.44% of the data is within 2 sigma of the mean. Okay, so you get that 68.26% that is in here plus a 13.59% in this little area here, and another 13.95, which is in that little area there. And as you go further out, you see that the percentages get smaller and smaller. So there's a smaller percentage of the data in each of these little areas that is farther and farther away from the mean. So how can we use this to do calculations? We're going to really do this in detail when we get on to box C, but a simple little calculation we can do is shown in this example. So at a high school, boys' heights are normally distributed with a mean of 174 centimeters and a standard deviation of 6 centimeters. Okay, so if you went and measured everybody, you would get 174 as your average, and if you calculated the standard deviation, it would be 6. So if there are 800 boys at the school, how many of them will be over 180 centimeters tall? Well, let's sketch a little normal distribution here so we can visualize these numbers a little bit better. Our normal distribution always looks like this. We know that our mean is at 174. And if our standard deviation is 6 centimeters, we can sort of approximately put a line here and a line here that is 1 standard deviation away from it. So this might be 6, and this might be 6 that way. So if we go up 6 from 174, that line is at 180. And if we go down 6 from 174, that line would be at 168. Okay. So we want to know how many boys are over 180 centimeters tall. We want to figure out, if this is 180 right here, we want to figure out how many people, how many boys would be in this area of the curve over here, okay, greater than 180 centimeters. Well, if we look at the previous diagram that we had, well, let's just write that down first. 180 is 1 sigma, or 1 standard deviation, larger than the mean. Now, if we think back to what we were talking about on the last slide, we know that that the mean is the same as the median. It basically divides this whole thing in half. So from here all the way up to our mean, we have 50% of our data, okay, because this is symmetric, right? And then, so 50% up to here. And then if we want to add in this other little part from our mean up to 1 standard deviation, we know from the previous slide that that is going to contain 34.313% of our data in that little area. Okay, because there's always 34.13% of the data between our mean and 1 standard deviation. So how much is in this blue shaded area over here? Well, all the data is 100%. We have 50% up to here, 34.13% up there. So what's left in this blue area must be 100 minus 50 minus 34.13, or 15.87% of the data is in that blue area. So 15.87% of boys are over 180 centimeters tall. How many boys does that correspond to? Well, we just have to do our quick little calculation here. We've got 15.87%, so if we do 0.1587, take our percent, turn it into a decimal, multiply by the number of boys, we get 126.96. So we can conclude that about 127 boys are over 180 centimeters. And we'll do a lot more calculations kind of similar to that when we get into box C.